We will now study the postsynaptic part of synaptic transmission, that is, the consequence of neurotransmitter binding to its postsynaptic receptors. To understand the operation of a glutamatergic synapse, we stage the following experiment. We record two connected neurons. This neuron here is called presynaptic because it's afferent to the neuron here, which is called postsynaptic. We record in whole cell configuration to record the activity of the whole membrane, and in current clamp mode to record membrane potential changes. If we apply a depolarizing current step here in the presynaptic neurons, which is called a stimulation, we record in response to this step an action potential here, and now in the recording here of the postsynaptic neuron, we record a response to the action potential, which is called an excitatory postsynaptic potential. It's a small depolarization of the membrane and transient, and you see here that it has a small amplitude. You have the scale here. It has 4 millivolt amplitude, and if you compare to the scale here, it's very small. To the scale of the action potential, it's very small, and it's transient. It's called excitatory because it's depolarizing, and when the membrane of the postsynaptic neuron is depolarized, it tends to activate sodium channels of the action potential. So the EPSP is a transient depolarization of the postsynaptic membrane. The EPSP that we recorded is a compound EPSP. Why is it a compound EPSP? You have it here in dotted lines. Because it's composed of different EPSPs. How do we know that? We know that because we have different blockers of glutamate receptor channels. Here is APV, it's one of these blockers, and when we add APV in the bus, as here, we stimulate the presynaptic neuron, we record the response in the postsynaptic neuron, and we see that the response has a very different decay phase, which means that there is an APV sensitive component. But still, the EPSP is still there. So what is underlying this EPSP that is APV resistant? If we had now another blocker of glutamate receptor channels, NBQX, at the dose of 1 micromolar, we don't have any response here. The EPSP completely disappears. Sometimes, when we applied APV plus NBQX, the EPSP does not completely disappear. There is a residual response. Let's have a look to this experiment again. In dotted lines, here is the control compound EPSP, and here is the APV resistant component. This APV resistant component can completely disappear in the presence of NBQX or not completely. The interpretation is as follows. On the top example, there are two different currents, glutamatergic currents, underlying the compound EPSP, one sensitive to APV and one sensitive to NBQX. In the example here at bottom, there are three types of glutamatergic currents underlying the compound EPSP, one sensitive to APV, one sensitive to NBQX, and one insensitive to APV plus NBQX. If there are several types of glutamatergic EPSPs, it's because there are several types of glutamatergic receptor channels. In fact, there are three types called by the name of the agonist which open them, the AMPA, the NMDA, and the kainate receptor channels. They are located in the postsynaptic membrane, sometimes only one of them, only the AMPA one, sometimes two of them, for example, AMPA and NMDA channels, and sometimes three, AMPA, NMDA, and kainate channels. In this chapter, we are not going to study kainate channels, we will only study AMPA and NMDA receptor channels. There is another type of glutamate receptor, which is called metabotropic receptor. This is not a receptor channel. so we're not going to study it in this chapter. On the top is a linear representation of a glutamate receptor subunit. There is an N-terminal and a C-terminal domain and 4 transmembrane segments. On the right, you see the protein inserted in the membrane. The N-terminal domain, followed by a ligand binding domain where glutamate and other agonists can bind, and then 4 transmembrane segments, one which is like a P-loop, and a C-terminal domain which is in the intracellular side of the membrane. We need 4 subunits like this to make up a glutamate receptor channel that you can see here on its closed state. So the pore is closed, and you see the 1, 2, 3, 4 subunits, and there are 2 receptor sites for glutamate. When the glutamate binds to these receptor sites, the channel opens and ions can go through. We see here the 3 types of glutamate receptor channels, the EMPA channels, kainate channels, and NMDA channels. They are named after the agonist that opens them. All of them are made up of 4 subunits like that. For EMPA channels, these subunits are called GLU-A1 to 4. There are 4 different, and then you have many combinations possible. The kainate receptor channels are made out of GLU-K1 to 5 subunits, and the NMDA receptor channel is made up of 4 GLU-N subunits from GLU-N1, GLU-2, A to D subunits. We will see that precisely later on. These subunits do not mix to each other, so EMPA are only made up of GLU-A, kainate of GLU-K, and NMDA of GLU-N. Though these subunits are very similar, they have a similar organization like this, but they never mix up to make a channel.